Okay, moving on to the chemistry of carboxylic acids and esters. So, carboxylic acids are weak organic acids. The equilibrium lies well to the left, meaning there are very few H+ ions in solution. Majority of the acid in the solution is undissociated, but despite being weak, carboxylic acids are able to liberate CO2 from metal carbonates. This is an equation you'll have met quite a few times before. Acid plus metal carbonate goes to give salt plus CO2 plus water. Okay, I'll give an example of this with an organic acid with a carboxylic acid. And this is propanoic acid. We add sodium carbonate. That will leave us with this salt here, which is a carboxylate salt, sodium carboxylate salt, and CO2 and water. Just a bit of balancing here. 2 there and a 2 there. Okay. The CH3CH2COO minus, that is what we call a carboxylate anion. Okay, carboxylic acids also carry out many of the reactions that you would expect of mineral acids like HCl and H2SO4. Let's just remind us of these. Acid plus alkali gives salt plus water. Acid plus a metal oxide gives salt plus water. And acid plus a reactive metal such as magnesium gives a salt plus hydrogen. Let's have a look at some reactions of carboxylic acids. The first one, and probably one of the more important ones, is the formation of esters. Esters are important chemicals and they are used as solvents, perfumes and flavourings. We'll have a look at this one here. We start off with our carboxylic acid and we add an alcohol in the presence of H+, then we form an ester and water. Okay, the oxygen actually comes from the methanol in this case, and this has been shown from some isotopic labelling studies. So start again with our carboxylic acid, which is benzoic acid, and if we label our oxygen, again, presence of H+ catalyst, then we get our ester. It's been shown, but it has been shown that this oxygen, here is from methanol because it contains the isotope. Okay, the catalyst is concentrated sulfuric or phosphoric acid. Okay, let's look again at this formation of esters. Let's look at some specific examples for formations of esters. We form esters through the reaction of a carboxylic acid plus an alcohol and that forms an ester and water in a condensation reaction in the presence of an acid catalyst, which remind again, it's concentrated H2SO4 or phosphoric acid. A couple of specific examples here. Let's start with ethanoic acid, and let's do it with a tertiary alcohol. Tertiary butanol. Let's do it with the simplest acid possible, methanoic acid. And propanol. So you need to be able to draw esters from combinations of acids and alcohols. Bit of a reminder on the naming of esters, which people do tend to find quite difficult. We just look at our generic scheme again, and we use an R on the carboxylic acid and an R on the alcohol. And we'll get our ester here. Okay, whichever part was oic acid becomes the OH part of the name. Okay, let's look at a couple of specific examples here. Okay, so looking at this one, if we put a ring around the bit that was the acid originally, this was the acid originally, it was originally benzoic acid, so that becomes benzoate. And then this part here, it's 3 carbons, was propanol, so that's going to become propyl, so propyl benzoate. Have a look at the simplest one, the simpler one. Okay, so this bit was ethanoic acid, so that's going to become ethanoate, and this bit was ethanol, so that's going to become ethyl, so ethyl ethanoate. Okay, so we can hydrolyse esters, they can be broken up. Hydrolysis means breaking bonds with water, it's an important definition for you to remember. Hydrolysis of esters can be achieved using either acidic or alkaline conditions. The acidic hydrolysis is essentially the reverse of esterification, and it settles at an equilibrium point with about 30% of the ester hydrolyzed. For this reason, we don't tend to use it, and we use alkaline hydrolysis, which is much more common and that uses sodium hydroxide. The general scheme for this here, we're going to illustrate it with ethyl butanoate. We add sodium hydroxide and we hydrolyse that to the sodium salt, sodium butanoate, and the ethanol. After the reaction mixture is cooled, then the sodium carboxylate salt can be readily converted into our acid. So let's take the one we've had earlier on. let's say we add HCl. Leaving us with an acid and salt. Hydrolysis is the basis of soap manufacture, which is called saponification. Fatty acids are esters of glycerol. So if we just look at what this looks like, here's our ester. This is our fatty acid. If we add sodium hydroxide to this, then we get glycerol. Which has a systematic name of propane 1,2,3 triol. And we get our carboxylate salt. The amount of sodium hydroxide needs to be carefully controlled because excess sodium hydroxide will be caustic. It is possible to use potassium hydroxide as well as sodium hydroxide. If we do hydrolysis with sodium hydroxide, we get solid soap. If we do it with KOH, we get liquid soap. And this is because the potassium carboxylate salts are more soluble in water. Okay, biodiesel. Biodiesel is a specific use of this hydrolysis reaction. It's made by hydrolyzing naturally occurring fats or oils to make fatty acids and then doing saponification with methanol. So if we add sodium hydroxide to this, then we get our glycerol again. Plus 3 lots of our carboxylate salt. We can then add methanol to this. And this is our biodiesel.